Hey there. We're going to go over a new concept called deriving equations. And up to this point, we've talked about some important words that we need to underline, and that's things like determine, explain, calculate, and now another one is called derive. So sometimes we're going to be asked to derive an equation, and we're going to work through a couple of examples and see what that looks like. So for this first example, it says we have a box. It has a mass m. It's pulled to the right by a spring with a spring constant of k. The box moves at a constant velocity v due to friction, and the coefficient of kinetic friction and static friction on the box are mu k and mu s, respectively. And then we're asked to derive an expression for the stretch of the spring, x, in terms of the given quantities and fundamental constants as appropriate. And so if you notice from this problem, there's no numbers. And so when we derive equations, we're not necessarily dealing with numbers, but we're getting multiple equations and we're kind of putting them together to come up with a new expression for whatever it is that the problem has asked me to solve for. And for in this one, it's the stretch of the spring x. And so to start out with this problem, we'll go ahead and we'll make a free body diagram of what's happening. So here is my object, and then the forces on this, we have a force of a spring that's pulling it to the right. And then we know that there is kinetic friction, and we know it's kinetic friction because it's moving at a constant velocity. And then we also know we have Fg going down, and then the normal force going up. And so I'm going to underline that word constant velocity. Okay, that word constant velocity means we have balanced forces. So let's make our net force equations. Okay, we have the net force in the x, and then the net force in the y. In the x direction, we have the force of the spring minus the kinetic friction, and that's going to equal 0 because of that constant velocity. In the y direction, we have Fg minus the normal force. That's also equal to 0 because we're balanced vertically. And so based off of these two net force equations, we know that the force of the spring is going to have to equal my kinetic friction, and my normal force is going to have to equal the weight. And so now we're going to start deriving. Okay, we know a couple equations that we've learned so far, and one is for the force of a spring. We know from that Hooke's law, the force of the spring is equal to kx. And we know our equation for kinetic friction, and that's equal to that mu k times the normal force. And so based off of this equation here, we can set those two equal to each other. And so that would give me kx is equal to mu k times the normal force. So all we've done here is we substituted this kx for your force of your spring and the mu k Fn for your kinetic friction. Okay, so we did a substitution there. Now, this normal force is not one of those fundamental constants. And so what we need to do here is we need to do another substitution. And we know that the normal force from our net force equation is equal to Fg. And earlier in the year, we learned that Fg is equal to mg. So we can do another substitution, and we can substitute Fg for this normal force. And so by doing that last substitution, we know that Kx is equal to mu k mg. And so now we can go ahead and rearrange this equation for the stretch of the spring. And so to do that, we're going to divide both sides by that spring constant. That cancels out there. And now my final derived equation, the stretch of the spring, is going to equal the coefficient of kinetic friction times the mg divided by your spring constant. And so now we've derived an equation for the stretch of the spring. And so notice we don't have any numbers, right? All we've done is we substituted in some different equations and we simplified it for the stretch of the spring. So let's look at another example. This one here, we have a baseball player that's moving with the initial velocity v naught. He slides to a stop on a baseball field. The coefficient of kinetic friction and static friction is mu k and mu s, and then we're asked to derive an equation for the acceleration of the player while he slides in terms of the given quantities and fundamental constants. And so let's go ahead and make a net force equation here and a free body diagram. So there's our baseball player. We know we have Fg going down and the normal force going up. And then he's sliding to the right, so we'll say that the friction is to the left. And since he's moving, we know it's kinetic friction. So we're going to be using that mu k here in just a little bit, not the mu s. And my net force equations, in the x direction, all we have is kinetic friction. And then in the y direction, we have the normal force minus the weight. That's going to equal 0. Okay, there's an acceleration horizontally and not vertically here. So we can set the vertical components there equal to 0. And so that just means that your normal force has to equal your weight, Fg. And so now we can go ahead and start doing some of our substitutions. We know an equation for friction, and that's equal to mu k times the normal force. And so we can substitute this in over here. So if we rewrite that, the net force in the x direction is going to equal mu k times the normal force. And my normal force is equal to the weight, and we know weight is equal to mg. So we can plug this in for my normal force. So let's go ahead and rewrite it. So your net force in the x direction is equal to mu k mg. Now for my net force, we learned a new equation recently, and that was Newton's second law. And that says that the acceleration is equal to the net force divided by the mass. If we rearrange this equation for the net force, I'll multiply both sides by mass to cancel that out. So your net force is just equal to mass times acceleration. So what we can do is we can plug this mass times acceleration in for your net force over here. So rewriting that, we now have mass times acceleration is equal to mu k mg. And if you notice, we have mass on both sides of the equation here. So we can cancel that out. And now we're just left with the acceleration is equal to the coefficient of kinetic friction times g. And now we have a derived equation for acceleration. So whenever we're working through these deriving equations, all the techniques and those algebra techniques that we're using, we're doing some substitutions, we're canceling things out. And it's important to notice that sometimes there's extra information. So the problem gave me mu s, but we didn't need it for this particular situation. So sometimes they might give you a quantity there that you don't need. So you need to realize that you're not going to use everything, but you'll use everything that's given appropriate to the problem, and then those fundamental quantities like our g here.